Class 11th Chemistry, Unit 8, Redox Reactions, and in this video we will discuss types of redox reactions. First come to combination reactions. A combination reaction may be denoted in the manner A plus B gives C. Either A and B or both A and B must be in the elemental form for such a reaction to be a redox reaction. All combustion reactions which make use of elemental dioxygen, that is O2, as well as other reactions involving elements other than dioxygen are redox reactions. For example, C plus O2 gives CO2. The oxidation number of carbon is 0, and in the product side, the oxidation number of carbon in CO2 is plus 4, that is carbon is oxidized. Now if you see, oxidation number of oxygen is O2 is 0, and oxidation number of oxygen in CO2 is minus 2. Decrease in oxidation number, that is reduction. Okay, so we can say this combination reaction is a redox reaction. In the similar manner, magnesium when react with the N2, this will form magnesium nitride Mg3N2. That is combustion of methane CH4, it gives CO2 and water. Again check whether this is redox reaction or not. Oxidation number of carbon in CH4, this is minus 4. Okay, and oxidation number of carbon in CO2, this is plus 4. This is increase in oxidation number, so this is oxidation. Okay, now oxidation number of oxygen in O2, this is 0, and oxidation number of oxygen in water, this is minus 2. This is decrease in oxidation number, so this is reduction. Okay, so this all the combustion reactions are redox reactions. Now decomposition reactions. Decomposition reactions are the opposite of combination reactions. A decomposition reaction leads to the breakdown of a compound into two or more components, at least one of which must be in the elemental state. For example, water decomposed to give H2 and O2. Just see the change in oxidation number. Hydrogen from plus 1 to 0 and oxygen from minus 2 to 0. Okay, in the similar way, this is decomposition of sodium hydride NaH to give Na and H2. This is decomposition of KClO3, potassium chlorate, to give KCl and O2. Now in this case, there is no change in the oxidation number of potassium. This is plus 1 in the reactant side. In the product side, this is plus 1. But if you see the oxidation number of chlorine, in KClO3, this is plus 5. But in KCl, this is minus 1. Okay, in the same way, oxidation number of oxygen in reactant side is minus 2. In the product side, this is 0. Okay. But all decomposition reactions are not redox reactions. For example, decomposition of calcium carbonate is not a redox reaction. See this reaction. CaCO3 gives CaO plus CO2. If you check the oxidation number of each atom on both the side, calcium plus 2 in the reactant side, in the product side, this is also plus 2. Carbon, this is plus 4 in CaCO3. Carbon in CO2, this is plus 4. Oxygen in CaCO3 minus 2 and oxygen in CO2 minus 2. So this is the decomposition reaction, but it is not a redox reaction. Displacement reactions. In a displacement reaction, an ion or an atom in a compound is replaced by an ion or an atom of another element. It may be denoted as X plus YZ converting into XZ plus Y. Displacement reactions fit into two categories: metal displacement and non-metal displacement. First come to metal displacement. A more reactive metal displaces a less reactive metal from its compound. See, these are the examples. Copper sulfate plus zinc converting into Cu plus ZnSO4. Now in this case, copper from plus 2 to 0, this is reduced. Okay, and zinc from 0 to plus 2, this is oxidized. In the same way, this is vanadium pentoxide. When reacts with the Ca, this will convert into V and CaO. In this case, this is vanadium from plus 5 to 0. Okay, and calcium from 0 to plus 2. This is TiCl4. When react with the magnesium, this will give Ti and MgCl2. Now in this case, Ti from plus 4 to 0 and magnesium from 0 to plus 2. Cr2O3 when react with the aluminium, this will convert into Al2O3 plus chromium. Now chromium from plus 3 to 0, decrease in oxidation number, and aluminium from 0 to plus 3, increase in oxidation number. So these displacement reactions are the example of redox reactions. Now come to non-metal displacement. The non-metal displacement redox reactions include hydrogen displacement and a rarely occurring reaction involving oxygen displacement. All alkali metals and some alkaline earth metals like calcium, strontium and barium, which are very good reductants, will displace hydrogen from cold water. See the reaction? Simply we can say when reactive metals react with the water, hydrogen gas is liberated. In the lower classes we have discussed. This Na when react with the H2O, this will convert into NaOH plus H2. See the change in oxidation number. Sodium from 0 to plus 1 and hydrogen from plus 1 to 0. The same way, this is calcium. It forms calcium hydroxide and H2 when react with the water. Less active metals such as magnesium and iron react with steam to produce dihydrogen gas. See, this is magnesium when react with the water. Okay, and when heat means water is in the form of vapors or in the form of steam. In the same way, this is iron. Change in oxidation number 0 to plus 3, and for hydrogen this is plus 1 to 0. Many metals, including those which do not react with cold water, are capable of displacing hydrogen from acids. Simply we can say when metal reacts with the dilute acids, hydrogen gas is evolved. These reactions are also the example of non-metal displacement reaction which are redox in nature. Dihydrogen from acids may even be produced by such metals which do not react with steam. Cadmium and tin are the examples of such metals. Like zinc, when react with HCl, it will form ZnCl2 plus H2. Now again see, zinc from 0 to plus 2. Increase in oxidation number is oxidation. And hydrogen from plus 1 to 0. Decrease in oxidation number, reduction. Magnesium plus HCl gives MgCl2 plus H2. Iron plus HCl gives FeCl2 plus H2. These reactions are used to prepare dihydrogen gas in the laboratory. Very less active metals which may occur in the native state such as silver and gold do not react even with hydrochloric acid. The oxidizing power of halogens decreases as we move down from fluorine to iodine in group 17 of the periodic table. This means that fluorine is so reactive that it can replace chloride, bromide and iodide ions in solution. In fact, fluorine is so reactive that it attacks water and displaces the oxygen of water. H2O when react with the F2, it will form HF and O2. Okay, this oxygen is obtained from this water when water react with the fluorine. It is for this reason that displacement reactions of chlorine, bromine and iodine using fluorine are not generally carried out in aqueous solution. Chlorine can displace bromide and iodide ions in aqueous solution. This is Cl2 when react with the KBr. From this KBr, Br is replaced by the Cl and we will get KCl plus Br2. The same way when Cl2 react with the Ki, I is displaced by Cl and we will get KCl plus I2. Now as Br2 and I2 are colored and dissolve in CCl4 can easily be identified from the color of the solution. Okay, so these reactions are used to identify Br minus and I minus in the laboratory through the test popularly known as layer test. These reactions can be written in ionic form like this. Cl2 when react with the Br minus, it will convert into Cl minus and Br2. When Cl2 react with the I minus, converting into Cl minus and I2. In the similar way, bromine can displace iodide ion in a solution like Br2 plus 2I converting into 2Br minus plus I2. The halogen displacement reactions have a direct industrial application. The recovery of halogens from their halides requires an oxidation process which is represented by this reaction. This is halide. It is converting into halogen by these oxidation process. Chemical means are available to oxidize Cl minus, Br minus and I minus. But there is no way to convert F minus ions to F2 by chemical means. Now what is the reason? Because fluorine is the strongest oxidizing agent. The only way to achieve F2 from F minus is to oxidize electrolytically. Now next, disproportionation reaction. Again, disproportionation reactions. In a disproportionation reaction, an element in one oxidation state is simultaneously oxidized and reduced. That is, same element oxidizes and reduces in the given reaction. That reaction is known as disproportionation reaction. One of the reacting substances in a disproportionation reaction always contains an element that can exist in at least 3 oxidation states. Okay. The element in the form of a reacting substance is in the intermediate oxidation state, and both higher and lower oxidation states of that element are formed in the reaction. For example, H2O2 when decomposed to give H2O and oxygen. Now let us see. Oxidation number of oxygen in H2O2 is -1. Clear? Peroxide. Oxidation number of oxygen in water is -2. This is decrease in oxidation number. So this is a reduction. But oxidation number of oxygen in O2 is 0. Again, if you compare this -1 to 0, increase in oxidation number, this is oxidation. So we can say oxygen of H2O2 is oxidized as well as reduced. Here, the oxygen of peroxide, which is present in -1 state, is converted to 0 oxidation state in O2 and decreases to -2 oxidation state in H2O. Phosphorus, sulfur and chlorine undergo disproportionation in the alkaline medium. See the reaction P4. This is alkali. This will convert into PH3 and H2PO2 minus. Oxidation state of phosphorus in P4 is 0. This is element. Okay. In the product side, in PH3, this is -3, and in this H2PO2 minus, this is +1. S8, oxidation number is 0. In the product side, this will form S2 minus ion. In its oxidation state is -2, and in S2O32 minus, its oxidation state is +2. In the same way, Cl2, in the alkali, it will give ClO minus, that is hypochlorite ion, and Cl minus, that is chloride ion. In hypochlorite ion, the oxidation number of Cl is +1, and in Cl minus, oxidation number is -1. Okay. So we can say the reaction of Cl2 with alkali describes the formation of household bleaching agents. Bleaching agents means which is used to decolorize. The hypochlorite ion formed in the reaction oxidizes the color-bearing stains of the substances to colorless compounds. That is, we can say, that is chlorine in alkaline medium acts as bleaching agent. Bromine and iodine follow the same trend as exhibited by chlorine. Fluorine shows deviation from this behavior when it reacts with alkali. When F2 in the presence of alkali, this will give F minus and OF2. And in both the cases, its oxidation number is -1. So we can say this is not the example of disproportionation reaction. Now why? Because being the most electronegative element, fluorine cannot exhibit any positive oxidation state. This means that among halogens, fluorine does not show a disproportionation tendency. Now let us see one question, problem 8.5. Which of the following species do not show disproportionation reaction and why? ClO minus, ClO2 minus, ClO3 minus, and ClO4 minus. Also write reaction for each of the species that disproportionate. Answer is among the oxoanions. These are the oxoanions of chlorine listed above. ClO4 minus, that is perchlorate ion, does not disproportionate because in this oxidation chlorine is present in its highest oxidation state, that is +7. The disproportionation reactions for the other three oxoanions of the chlorine are as follow. ClO minus, in this oxidation state of Cl is +1, and products are Cl minus, oxidation state is -1. In ClO3 minus, oxidation state is +5. Okay. In case of ClO2 minus, oxidation state of chlorine is +3. In the product side, it will form ClO3 minus, oxidation state is +5, and Cl minus, oxidation state is -1. In the same way, ClO3 minus, oxidation state of chlorine is +5, and this is changes to -1 and +7. So we can say for the disproportionation reaction, element must show at least 3 oxidation state. And in the reactant side, the oxidation state of the element should be intermediate. Now problem 8.6. Suggest a scheme of classification of the following redox reactions. N2 plus O2 converting into 2NO. Combination is taking place. So this is the example of combination redox reaction. This is lead nitrate converting into PbO plus NO2 plus O2. Single substance is decomposing, breakdown into the smaller. So this is the decomposition redox reaction. This NaH plus H2O converting into NaOH plus H2. This is the example of displacement redox reaction. NO2 plus OH minus converting into NO2 minus plus NO3 minus plus H2O. Now just see the change in oxidation number of nitrogen. In NO2, oxidation number of nitrogen is, we can say for oxygen, for each atom of oxygen, this is -2. And for 2 oxygen, this is -4. So we can say this for nitrogen, this is +4. Now in this is X plus 2 multiplied by -2, and this is equal to -1. So what the value of X? X is equal to, we can say -1 plus 4, and that's why this is +3. Okay. Now in this NO3 minus, nitrogen is X plus, this is 3 multiplied by -2, and this is equal to -1. Now what the value of X? This is X is equal to -1, and 3 to just 6. This side, this will go +6. So this is +5. So you can say that is +4 is changing into, this is +3 in this case and +5 in this case. Oxidation and reduction simultaneously taking place. So this is the example of disproportionation redox reaction. Okay. Thank you.